Rings are an algebraic structure. They are similar to groups in some ways, but they are more complex. Whereas groups are a set with an operation on them on it that has to satisfy certain properties, like being associative, having an identity, and so forth. Rings have two operations. Now, we will almost always use multiplication and addition as our two operations on rings. There will be the occasional example where we use something else, but those will be fairly rare. And when talking about abstract rings, we will pretty much exclusively use addition and multiplication for the two operations that we look at. Most of the groups that we saw in the last semester are also rings. Most of them also have a second operation that you can include that turns them into this more complex structure. Now, with this more complex structure becomes a lot more ways to reason about things and argue about things. And indeed, rings are more common for us to work with in areas outside of abstract algebra. And so rings are a fruitful area for us to start looking at here. So let's look at definition 85. This is on page 55 of the notes. This is a very important definition. It's going to describe rings, which are going to be our primary object of study for at least the first half of the course. So definition 85. A ring is a set R. We often use an uppercase R, S, and T for rings. A ring is a set R with two binary operations. Binary here meaning that each operation takes two inputs. Two binary operations, addition and multiplication, such that for all A, B, and C belonging to the ring R, we have the following properties. And just like for groups, we're going to describe properties that the addition operation has to satisfy, properties that the multiplication operation has to satisfy, and we're going to define how the two operations have to interact with one another. So the first requirement is that addition is associative and commutative. In a ring, addition is always commutative. So in other words, this is saying that for all A, B, and C that lie in R, we have that A plus B plus C is equal to A plus B plus C. That's associativity. And A plus B equals B plus A. So the addition operation is associative and commutative. Number two, there exists an additive identity. Now, because all of our rings always have additive identities, and we're going to use addition as our operation, again, nearly always, we are going to use 0 as our additive identity for general rings. So there exists an additive identity 0 belonging to R, such that A plus 0 equals A, which is equal to 0 plus A, and this is true for all A's. This is just saying that 0 is an additive identity. Furthermore, there exists additive inverses. That is to say, for all elements A belonging to R, there exists an element negative A in R, so some element which we denote as negative A, such that A plus negative A is 0. So the operation of addition has additive inverses, or every element has an additive inverse. Furthermore, when we have some expression like a plus the additive inverse of b, we usually write that as simply a minus b. Technically, subtraction is not generally studied as its own operation because it's not even associative, but we'll usually use the standard abbreviation of a plus negative b being written as a minus b. So these are the 3 requirements that we have for addition. We still have the requirements for multiplication. But we can point out already that if we look at these 3 requirements, then they look very familiar. In fact, we could have abbreviated this, and a useful way of thinking about things sometimes is the following. This means that R is an abelian group under addition. Now, as we're going to see, rings do not need to be groups under multiplication, not at all. But every ring is an abelian group under addition. So one can think of rings as being built up from abelian groups by starting with such an abelian group and then defining some sort of multiplication on it. It's going to turn out that the set of integers is a ring under the standard addition and multiplication. We've already studied the integers as a group under addition extensively. So we can think of its construction as a ring as coming from starting with the set of integers as a group and then defining multiplication in the standard way on top of that. And as long as that multiplication satisfies the requirements that we're about to write down, which we'll see that they will, then that turns the integers into a ring. So we could say that R is an abelian group under addition. Any ring R is an abelian group under addition, which actually means that addition is pretty restrictive. It has lots of requirements: associative, commutative, having identity, having inverses, things like this. Multiplication, on the other hand, is far less restrictive. We have very few requirements for multiplication. In fact, we only have 1. The only requirement we have for multiplication by itself is that multiplication is associative. That is to say that if I have A times B times C, that equals A times BC. Oh, as I'm doing here, we use concatenation to mean multiplication always. So this is the only requirement we have for multiplication, other than it being an operation, which implies that, of course, the ring, the set R is closed under multiplication. Other than that, we only require multiplication to be associative. Notice in particular the things that we don't require here. We don't require the ring to have a multiplicative identity. The element 1, the identity for multiplication, doesn't necessarily need to exist in the ring. And so because the identity doesn't even need to exist, inverses don't need to exist. In fact, even when the identity does exist, the multiplicative identity does exist, most rings will not have inverses for every element. And we certainly don't require that multiplication be commutative. The A times B can be different from B times A in arbitrary rings. So it looks like we have very, very little to say about multiplication. However, our last condition is called the distributive condition, and it really does help to tie things together because it tells how multiplication and addition play with each other. It tells us what happens when we've got an expression that involves both an addition and a multiplication at the same time. So condition 5 is that multiplication is distributive over addition. Which is to say that if I have A times B plus C, this equals AB plus AC. So we've multiplied A on the left, and when doing that, that's equal to the expression we get when we take A multiplied by each of the summands inside. And we have that if we have the expression A plus B, which gets multiplied by C, that's going to be equal to AC plus BC. Now, of course, the reason why we need both of these conditions is that multiplication is not assumed to be commutative. So A times B plus C is not the same as B plus C times A necessarily. So these are the 5 conditions that we need. We need the ring R to be a group under addition, and then we need these 2 conditions regarding multiplication. The first, that multiplication is associative, and the second, that multiplication is distributive over addition, or multiplication distributes over addition. The multiplication operation on the integers certainly satisfies these 2 conditions. We know that multiplication is associative. It doesn't matter how you group it up. In fact, we know more. We know that multiplication of integers is commutative, but that's not part of the definition of a ring. And we do know that distribution works when you multiply integers together. So the set of integers was sort of our prototypical example of a group, the set of integers with addition. It's also our typical example of a ring. The set of integers with integer addition and multiplication is an excellent example to keep in mind when we're starting to learn things and prove things about a ring. However, it should be cautioned that just like with a group, the integers have many special properties as a ring that not every ring enjoys. The set of integers happens to be particularly nice among rings. It has several properties that make it easier to work with. Now, in finishing up this definition, I want to give a couple of terms that we use to describe rings that have some additional properties. So when we had a group that had an operation that was commutative, we called it an abelian group. We're going to have some similar adjectives that we can attach to groups to describe various properties that they have with regards to these various operations. So the first one is that if multiplication is commutative, that is to say that if A times B equals B times A for all A and B in the ring R, then R is called, unsurprisingly, a commutative ring. Commutative rings have this property that their multiplication is commutative. They are in many ways easier to work with because you don't have to worry about the order of multiplication. Whereas if you are working with a non-commutative ring, or a ring where you don't know if it's commutative or not, you have to be careful and make sure that the order of multiplication always stays the same. If the ring R has a multiplicative identity, we write it as 1. So that is to say that 1 times A is equal to A, which is equal to A times 1 for all elements A in R. So sometimes the operation of multiplication will have an identity. In fact, in many cases that we care about, a ring will have an identity. We call a ring with such an element 1, as long as it's different from 0, a ring with identity. So I'm going to come back and talk about this 1 not equal to 0 business in a moment. This is actually not a great restriction. This just means that we're not looking at some trivial cases, or really one particular trivial case. We will often be working with rings with identity. When we're working with a ring with identity, we know that there's this element 1 in it that behaves as a multiplicative identity. 1 times A is A, which is A times 1. Furthermore, in those cases, in rings with identity, we will often be a little bit careless with our notation, and we might use the symbol 2 to mean 1 plus 1, the symbol 3 to mean 1 plus 1 plus 1, even if our ring is not the integers. We'll try to be careful about that in this course, though. All right, so then moving on further, if R is a ring with identity, and A is an element of R, such that there exists some other element, or perhaps the same, but there exists some element of R such that A times B equals 1, then A is a unit of R and B is equal to A inverse. Or rather, we write B as A inverse. So notice here that we're using the multiplicative inverse notation to mean the multiplicative inverse within a ring, so raised to the -1. And we're using the additive inverse notation, that is the negative in front, the negative sign in front of the symbol, to mean the additive inverse. We do need to make sure to keep these distinct from one another because the additive and multiplicative inverses of an element are almost never the same. We could treat this a different way. We could say R is a ring with identity. If R is a ring with identity, then an element is a unit if it has an inverse. Now, if it has an inverse, then that means essentially you can divide by it. For a typical ring will have a collection of units. If it's a ring with identity, we'll have a collection of units, but that collection of units will typically be a small subset of the whole ring. Your typical ring contains many, many, many elements which do not have inverses. We'll be looking at a certain class of rings where every possible element has an inverse, and those have a special name, and we're going to spend quite a bit of time talking about them later. Those are called fields. But a typical ring will have some units and a lot of non-units, typically. All right, so want to see what we can do, what we can play around with, just looking at these definitions. And in particular, I want to note that this condition 1 not equal to 0 in the description of the multiplicative, or the ring with identity definition, rather, is really only eliminating a special case. So our first example, but it almost doesn't even count, is called the trivial ring. The trivial ring is the ring R, which contains just a single element, 0, where 0 plus 0 is equal to 0, and 0 times 0 equals 0. There's just the one element, it just sits there. We had the trivial group that we looked at last semester, which contained just a single element. The trivial ring also contains just a single element. Now, technically, this ring R has identity. So 0 itself is a multiplicative identity, because when you multiply it by anything in the ring, that is 0, you get that thing back, 0. So technically, in this ring, 0 is a multiplicative identity, but it's a multiplicative identity for a silly reason. It's a multiplicative identity because there's only one element in the ring, and no matter how you combine two zeros together, you get another 0 in this ring. So we have a multiplicative identity. I should write here, it has a multiplicative identity, but that multiplicative identity is 0, which is also the additive identity. So in this case, we basically have that 1 equals 0, where I'm using 1 here to stand for the multiplicative identity of the ring and 0 to stand for the additive identity of the ring as normal. So the takeaway for of this example is that in the trivial ring, we have the two identities being equal, the additive and the multiplicative being equal. However, if you have any non-trivial ring, this cannot happen. In any non-trivial ring, the additive identity and the multiplicative identity will not be the same. Let's see that if a ring has 1 equals 0, then it is trivial. So we claim if R is a ring with the multiplicative identity 1 equaling the additive identity 0, then the ring is the trivial ring. So let's let A be any element of R. What we're going to do is we're going to prove that A is equal to 0. And since we let A be any element of R, that means that every element of R is 0, so there's only the one element. So I wanted to go through this so that we can see some of the tricks that we use, some of the techniques that we can often use in working out some of the basic theorems that we have involving rings. So we have that A is equal to A times 1. This is part of the definition of being the multiplicative identity, is that A is equal to A times 1. But we know that A times 1 is the same as A times 1 plus 0. Where we can do this because 0 is the additive identity, and so 1 plus 0 is equal to just 1. So now we can use distribution. Most of the time when you're trying to prove a basic fact about rings, something to do with how the various properties interact, you should be on the lookout for where you're going to be using distribution, because it really is the key fact and key assumption that weaves the addition and multiplication together and makes a ring and not just a set with two operations on it. In this case, the distribution is going to help us by allowing us to write a times 1 plus 0 as a times 1 plus a times 0. So now a times 1 we know is just a. That's the multiplicative identity. A times 0 we're going to write as a times 1. Because we know that 1 is equal to 0. That was our assumption. And again, a times 1 is equal to 1. These are pretty basic things that we've been doing, but they're important for establishing the result. So now we have that a is equal to a plus a. Now there are a few ways that we can think about the next step. One way is to think of the following, that this means that on the left we could change the left-hand expression from a to a plus 0, and we have a plus 0 is equal to a plus a, and so by cancellation we have that 0 equals a. Now, cancellation was a property that we talked about for groups, which said that, if you have AB equals AC, then B has to equal C if all your elements come from a group. And since the ring is a group under addition, that means that when you're just looking at things involving addition, it behaves exactly the way an abelian group does. So in particular, it satisfies the cancellation property. Another way that we could do it, which is perhaps more familiar to us from algebra that we've seen before, is we can subtract. We can simply subtract a from both sides. So subtracting a from both sides, technically this means adding negative a to both sides, adding the additive inverse of a to both sides. We get that a minus a is equal to a plus a minus a. So a minus a is 0, and a plus a minus a is equal to a. Now again, if we want to be technical about this, which is helpful sometimes, we would write it out this way. Subtracting a means adding the additive inverse of a. So we get a plus negative a is equal to a plus negative a. Now we know that the sum of any element with its additive inverse is the additive identity, that is 0. And then over here on the right, we can group up by associativity our elements any way we want. And so in particular, we have that this part is 0, a plus negative a is 0, and so we have that 0 is equal to a. So the white text that we have here is not being as precise as we might. One of the blue text or the red and green text would be more precise for what's going on. However, subtracting in a ring works exactly as you expect it to. You have to be careful with multiplication, but the addition works basically how you think it should if you just use your intuition from the integers. So that finishes up this claim. So the only ring that has an additive and multiplicative identity being the same is the trivial ring. Okay, let's stop looking at trivial examples and let's start looking at a variety of more interesting examples. So let's look at some examples of rings. So an example would be the integers under addition and multiplication. So I've already mentioned this. This is sort of our typical example. This was our typical example of a group. This is also our typical example of a ring. If you have an idea about how rings might work, the first example that you want to think of to see whether what you're saying makes sense is the integers. It's got the addition, the multiplication distributes over the addition appropriately, everything's associative, everything's commutative. In fact, this is a commutative ring with identity. Because there is an element of this ring which acts as a multiplicative identity. Now that element is exactly 1, which is part of the reason why 1 is our standard notation for such a ring. It's commutative because multiplication is commutative, and it's with identity because it has a multiplicative identity 1. That is not 0. The units of this ring Z are 1 and -1. These are the only two elements of the ring which have multiplicative inverses. Now, the multiplicative identity itself is always a unit. So note that the multiplicative identity, if it exists, is always a unit. Since 1 equals, or rather 1 times 1 equals 1 by definition. In many rings, -1 will be an example of another unit. However, the element -1 can look different in different rings, and sometimes it's -1 and 1 are the same thing. So you're always guaranteed at least 1 unit if you have identity, but not necessarily more than that. Let's look at what comes next. Let's look at 2z, which is the set of even integers. So 0, 2, 4, 6, 8, etc., etc., -2, -4, -6. Let's check and see whether this is a ring. So first of all, we need to check and see whether this is a group under addition. Well, it's certainly closed under addition. Addition is certainly associative on this set because it's associative on the integers, which this is a subset of. It has an additive identity of 0, and every element has its additive inverse because the negative of an even number is an even number. So that means that 2z with addition is a group, is an abelian group. So that takes care of the first 3 requirements in the definition of being a ring. Now we need to make sure that there's a multiplication. So multiplication does work here because if I multiply any 2 even numbers together, I get another even number. So the set 2z is closed under multiplication. And multiplication is still associative. So multiplication is associative. And it does, in fact, distribute over addition. And distributes over addition. And for this set, the fact that multiplication is associative and distributes over addition is pretty much something that it inherits from the fact that it's the same multiplication as in the integers z. It's just working on a subset of them. However, notice that 2z is commutative, but without identity. Remember that when we talk about a ring having identity or not having identity, we're always talking about the multiplicative identity. So the ring 2Z here does not have a multiplicative identity element. There's no element of this ring that you can multiply by another one and get back that second element. It's a subset of a ring that does, so 2Z is a subset of Z. Z has an additive identity, or sorry, multiplicative identity. They both have additive identities of 1, but 2Z does not contain that one, and it doesn't contain any other ones. This is an example of a ring that is commutative, but not with identity. Let's look at the rings Z mod NZ, which we looked at extensively in the last semester. So Z mod NZ with n a positive integer these are all rings with addition and multiplication essentially mod n. So if I take two elements, so for a sub-example, if I look at Z mod 10Z, I can look at the elements 3 bar and 7 bar, meaning the equivalence classes of 3 and 7 under the equivalence relation of being equivalent modulo 10. And I can multiply them. And the way multiplication in this ring works is that you multiply the two representatives that you're working with and then take the equivalence class of that representative. So 3 bar times 7 bar is 21 bar, which of course we can simplify because 21 is equivalent to 1 modulo 10 because their difference is a multiple of 10. And that's how the multiplication in these rings works. So the Z mod NZ are all commutative rings with identity, with the identity 1 bar. I really should specify here, it's a minor thing, but the n that we're working with really has to be greater than or equal to 2 for this statement here to be correct. So these are all commutative rings with identity 1, with addition and addition and multiplication modulo n, as specified above here. And what our computation above showed is that in the ring Z mod 10Z, the elements 3 and 7 are units. And in particular, this shows that 3 is the inverse of 7, and 7 bar is the inverse of 3 bar in these rings. Notice in particular that the notation of this inverse 1 can't move inside the bar notation that we have here. So this doesn't work. It doesn't work to say something like 3 bar inverse is 3 inverse bar, which is 1/3 bar, and now we've broken everything because the equivalence relation being denoted by this bar is only on integers, and so this doesn't work at all. So that notation cannot move inside the bar. However, 4 bar is not a unit. Now, in this small example, the easiest way to work that out is to multiply 4 by all the different elements of Z mod 10Z, and notice that none of them turn out to be 1. You can find a an argument in the notes that uses a more sophisticated type of argument that doesn't require you to try all the different elements, which is helpful if n was much larger. You certainly wouldn't want to do this with z mod 230z or something like this. But here we can just try a bunch of times. 4 bar times 0 bar is 0 bar. Well, we knew that because 0 bar is going to be the additive additive identity. We haven't proved it yet, but we will prove that anything times the additive identity 0 is always 0 again. 4 bar times 1 bar is since 1 bar is the additive identity, it's just 4 bar back. 4 bar times 2 bar is 8 bar. 4 bar times 3 bar is 12 bar, which is 2 bar. 4 bar times 4 bar is 16 bar, which is 6 bar. 4 bar times 5 bar is 20 bar, which is 0 bar. This is an interesting phenomenon here that we're going to look at in a moment. Here we took two things that were not equal to 0, multiplied them together, and got 0 out of it. This is not something that occurs in the integers, but does occur here. And studying when that does and doesn't happen turns out to be very important in understanding the structure of rings. But continuing on, 4 bar times 6 bar is 24 bar, which is 4 bar. 4 bar times 7 bar is 28 bar, which is 8 bar. 4 bar times 8 bar is 32 bar, which is 2 bar. And 4 bar times 9 bar is 36 bar, which is 6 bar. So in particular, you'll notice that none of the possible things that you could get by multiplying 4 by something in the ring are the additive identity. It is not possible to multiply 4 bar by something and get 1 bar out of it in this ring, as we've just demonstrated by searching. That means that 4 bar is not a unit. In fact, determining the elements of z mod nz which are and are not units is a valuable exercise that you'll be looking at. All right, let's look at some more examples. We won't go through some of the others in quite as much detail. I'll leave some of those for examples. Let's look at the set Q. The set Q, the set of rational numbers, is a ring which is commutative with identity. Furthermore, if A over B is in Q is not 0, then we have that A over B times B over A, which is also an element of Q, is equal to AB over BA, where A and B are both integers, which is just 1. The identity, the multiplicative identity. So in particular, what this shows is that every non-zero element of Q is a unit. Every non-zero element of Q has a multiplicative inverse. This is a special case. Most rings, as I mentioned, have a few units and lots of non-units. Q, it doesn't have that. Q only has one element that's not a unit, that is 0, and every other element is a unit. I should mention, and there's an argument for this in the notes, that in a non-trivial ring, any non-trivial ring, the additive identity 0 is never a unit. So let's note, if 1 is not equal to 0, then 0 is never a unit. So it's just not possible to divide by 0. Every non-zero element of Q is a unit. This makes Q special, and there's lots of things that you can do here. It makes solving equations, for instance, in the rational numbers very easy. I know that if I have a times x equals b, and a and b are rational numbers, then I can always just divide by a. I can always, or in other words, multiply by a inverse. And so I can conclude that x is equal to b over a, or a inverse times b. I can always solve equations like this, solve linear equations like this. Whereas that's not necessarily true in the integers. If I choose random numbers for a and b, this equation is not solvable in the integers, typically. But over Q it is. We have a special name that we give to rings that have these nice properties that Q does, that the set of rational numbers does. So that's a definition 86. A ring F is a field if F is a commutative ring with identity and every non-zero element is a unit. Fields are very nice to work with. They have a lot of structure to them, a lot of properties, lots of equations that can be solved, and so forth. We're going to be referring to fields quite a lot, even as we're studying general rings, but we're also going to study fields in earnest later in the semester when we look at some interesting connections that fields have with groups. We could think of fields and groups almost as being on a couple of ends of the spectrum of algebra in terms of how nice they are and how much structure they have. Groups have just the one operation, and so not a lot of structure, not a lot of operations to work with. Fields have two operations, and those operations have to satisfy a lot of requirements, so there's lots of things you can say about them. And yet, there are a lot of very interesting connections between those, but we will get to those at a later point. All right, so let's look at some other examples of fields. Now, every field is a ring. It's a ring with special properties, but the rings of the real numbers and the complex numbers are also fields under standard multiplication and standard addition and multiplications. These are far from the only fields. There are many, many, many fields that we work with, but these three fields, the rational numbers, the real numbers, and the complex numbers, are the ones that we're most familiar with and the ones that you should sort of keep in mind, intuit when someone says, let me take a random field, unless they specify some other properties of them. So the sets of real numbers and complex numbers are also fields. All right, so let's look at a type of ring that we're going to be working on quite a lot. The set Q adjoin X. And this notation right here refers to the set of polynomials with variable x and coefficients in Q. So polynomials using x as the variable and where all the coefficients are rational numbers, the set of all of those polynomials is a commutative ring with identity. And it contains elements like 2 plus x plus 3x squared, 1 half x plus 4x cubed, 7, 0, and x plus 1. So, set of all polynomials here. And so let's identify the units. This is a ring with identity, where the identity polynomial is 1. We're operating under standard polynomial addition and multiplication. I should specify that. Under polynomial addition and multiplication. And furthermore, we have units. And the units of q adjoin x are going to be those polynomials that you can multiply by some other polynomial in order to get back to the element 1. Now, if we think about this a little bit, we can see that if we take a couple of polynomials with positive degree, or if even one of the polynomials we multiply has positive degree, then the result will have positive degree. Because you find the degree of a product by adding the degrees of the polynomials that you started with. And so that means that if we take any polynomial that isn't a constant, that has degree greater than 1, it can never be a unit. Because if you multiply it by anything else, you'll get something with positive degree, and the identity element does not have positive degree. It has degree 1 as a polynomial. So the units of q of x are the non-zero, because remember 0 is never a unit, are the non-zero constant polynomials. So here's a ring that we built up out of a field. We use the field Q in order to build it, but even so, a lot of the elements of this ring are not units, and only a few of them are. And then we can go further with some more examples. So we can look at the set MNR of n by n matrices with real coefficients is a ring under matrix multiplication and addition. I should say addition and multiplication. This ring, MNR, is non-commutative. We know that matrix multiplication is not commutative. If you multiply matrices 2 different ways, you get different matrices out of it. So MNR is not commutative. However, it does have an identity. And the identity is the n by n identity matrix which is why it's called the identity matrix, because if you multiply this by any other n by n matrix, you just get that one back. It is the multiplicative identity under matrix multiplication. And then the units of MNR are the matrices with non-zero determinant. Because a matrix with a non-zero determinant has an inverse. In other words, these are the non-singular matrices. Or, in other words, this is the same as the general linear group that we looked at before, as a set anyway. And this suggests something that we'll look at more at a later point, but the units of a ring taken all together are indeed a group under multiplication. They won't typically be a group under addition anymore. They won't typically be closed under addition, but they will be a group under multiplication, and this is one of the best examples of that, or the place where we can see it the most. Okay, let's look at another example. The set C of R of continuous functions from R to R is a group under addition, let me be more precise, pointwise addition, that is standard addition of functions, and composition. Sorry, I shouldn't say composition. Pointwise addition and multiplication. Sorry. It's actually not a group under composition because one of the distributive laws doesn't hold with composition. And if you want a neat little exercise, go ahead and check that. But the set of continuous functions from R to R is a group under pointwise addition and multiplication with identity, the constant function 1. And this is commutative because pointwise multiplication of functions is commutative. I need to go on to the next theorem. We're going to do one theorem today which establishes the basic properties of or some of the more useful properties of rings, ones that we're going to use over and over again, usually without specific citation to this theorem. So theorem 87. So let's let R be a ring, and let's let A be an element of R. So the first one, I mentioned this earlier. If I take any element of a ring and multiply by the additive inverse, I should get the additive inverse back. No matter which side I multiply it on. So this is very intuitive. This is exactly what we think should happen when we multiply by 0. When we multiply two things and one of them has a negative on it, the point is it doesn't matter where that negative sign goes. Right now we're talking about the inverse of the additive inverse of b, or negative b. That's the same as if I attach it to the a, and it's the same as if I put it on the outside of the whole thing. So in particular, this is why we can write, although we'll often want to be more precise than this, we can write negative AB without putting any parentheses on, and it means any one of these three because they're all equal. Number 3 is that if we take two negatives, they cancel each other out. So negative A times negative B is equal to A times B. Number 4, if we take A times B minus C, this is equal to AB minus AC, and B minus C times A is equal to BA minus CA. So in other words, multiplication distributes over subtraction, just like it distributes over addition. Note that I am being very careful to keep the order of multiplication the same. On the left here, we have that A is on the left. The b and c are both on the right of that multiplication. When I distribute the a through, that same order is maintained. A is on the left, a is on the left. Similarly here, a is on the right, and when I distribute, a is on the right. So if R has identity, that is if 1 belongs to R, then if we take -1 times a, that equals -a, and -1 times -1 always equals 1. So -1 is always a unit. I waffled on that a bit earlier, but here's the statement that says that -1 is in fact a unit. It does require a little bit of argument, and in fact its inverse is -1. And then finally, if 1 is in R, then the multiplicative identity and inverses are unique. All right, we'll talk about how to do a couple of these statements just to show you what the pattern of argument looks like here. The rest of them will be left as an exercise. I will point out that number 6 here that we just mentioned, the argument for this goes almost exactly like the argument we did for groups when we wanted to show that the identity was unique and inverses were unique. So let's look at the proofs of a couple of these statements. All right, so for part 1, remember that was that a times 0 equals 0, which is 0 times a. So let's let a belong to the ring R. We have that 0 plus a times 0 is equal to a times 0, because 0 is the additive identity, which is a times 0 plus 0, which is a times 0 plus a times 0. This is using a very similar argument to the one that we did before when we were looking at trivial groups, or trivial rings, rather. So if a is in R, then we have this string of equalities. So that means that 0 plus a times 0 is equal to a times 0 plus a times 0. And by cancellation, we can do cancellation for addition, but not multiplication. We'll see why in a second. By cancellation, we have that 0 is equal to a times 0, where we've canceled these two summands. And then a similar argument shows the other direction, almost exactly the same. Let's look at part of number 2. We want to show that a times negative b is equal to negative ab. So remember, again, when working with additive inverses or negatives, things like this, we can use many of the techniques that we had for groups and many of the proof strategies that we had. In order to show that a times negative b is equal to negative ab, it suffices to show that a times negative b plus ab is the identity. If this is the case, then that means that a times negative b is the additive inverse of the product ab. So we have that a times negative b plus ab. Now we can use distribution backwards. Just like in normal algebra, the distributive law works both ways. So because we have a times negative b plus a times b, that's the same as a times negative b plus b. Now we have an element being added to its additive inverse. So that means that this is a times 0. And by part 1, we know that a times 0 is 0. So that means that a times negative b and ab, product ab, are additive inverses of each other. So in particular, this means that a times negative b is equal to negative ab. And similar sorts of arguments work for the other 4 parts of the theorem. And some of those will be exercises. Now, it's easy to want to use some of the techniques that we just did, such as cancellation, when working with multiplication in rings, and that's where we have to be very careful. In general, rings do not have a cancellation law. Elements do not necessarily have multiplicative inverses, even if the ring itself has a multiplicative identity, which it may not. So we have to be careful. Let's look at an example to see why we have to be so careful about this. Let's let R be the ring Z mod 12Z. Now, we have that 3 bar times 7 bar is equal to 21 bar, which is the same as 9 bar. Furthermore, we have that 3 bar times 3 bar is equal to 9 bar. So that means that we have 3 bar times 7 bar is equal to 3 bar times 3 bar. And so we have these two products being equal. They're both equal to the equivalence class of 9. But 7 bar does not equal 3 bar. Those are just two different elements of the ring. In particular, this means that we're not allowed to do some sort of cancellation here, where we cancel out the 2 3s on the left. That just doesn't work. So this means that cancellation doesn't work. In this particular ring, and there are many rings where it doesn't work most of the time. There are rings that we're going to study in the very next section where cancellation does work, as well as many other things, and they have lots of nice properties. But you need to know something about the ring before you can use any sort of cancellation rule. And in particular, we can't divide both sides by 3 either, because 3 doesn't even have a multiplicative inverse in this ring. You can check it the same way that we checked for 4 in the previous ring, Z mod 10Z. There's just nothing you can... 3 is simply not a unit in this ring, and therefore you can't divide by it. Division is not an operation on a ring. You always have to multiply by an inverse, which means first you have to check and see whether an inverse of that particular element even exists. And much of the time, it will not. All right. So, this is going to... this is going to be where I end it. We're going to use this example that we just had of wanting to have cancellation but not having it in order to motivate our next definitions and theorems and the types of rings that we look at there.